All right, welcome to the AI Research Roundup. I'm your host, Alex. Today is May 7th, 2025, and we're looking at an ICLR conference paper published just over 3 months ago called Feedback Schrödinger Bridge Matching. This paper tackles transforming data between different sets, or distributions, using what are known as diffusion bridge matching frameworks. These frameworks learn a path, or a transport map, to change one dataset into another. The problem is, current methods are often too slow or need all data perfectly paired. So this paper introduces Feedback Schrödinger Bridge Matching, or FSBM, a new semi-supervised approach. This means it cleverly uses a small set of pre-aligned data pairs, called the key point set, to guide the transformation for other, non-coupled samples. So this first figure really sets the stage for understanding where Feedback Schrödinger Bridge Matching fits in. It visually places Feedback Schrödinger Bridge Matching as a flexible approach connecting two extremes. On one side, there's what's called DSBM, which operates with 0 pre-aligned data pairs. On the other extreme, you have I2SB, where all data pairs are perfectly aligned beforehand. Feedback Schrödinger Bridge Matching, their method, works with a variable percentage, K% as they call it, of aligned pairs, bridging that gap by using that partial information effectively. Okay, so building on that idea of using a small set of aligned data, this next figure visually unpacks how these key point pairs actually work. We see a blue area, the source distribution, that's our starting collection of data, and a green area, the target distribution, where we want that data to transform. Within these, you have these matched key point pairs, and each pair has a region of attraction around it. This visualization highlights how these key points influence nearby data points, essentially guiding their transformation by helping to preserve their relative distances. Alright, so these key points help guide the transformation. Now, this figure really shows this in action with a crowd navigation task, which is essentially guiding a group of data points through tricky obstacles, like an S-tunnel or a V-neck shape. We see how Feedback Schrödinger Bridge Matching, on the bottom, compares to another method, GSBM, on top. Especially under perturbed conditions, meaning the initial yellow starting points are a bit scattered or off-center, Feedback Schrödinger Bridge Matching generates much smoother paths, leading the navy-blue generated points effectively to the red target, unlike the more dispersed results from GSBM. Now, to put some numbers to those crowd navigation paths we just saw, this table quantifies that performance. It shows the W2 distance. That's a mathematical way to measure how different the generated data is from the ideal or ground truth distribution, with lower numbers being better. We're comparing GSBM against Feedback Schrödinger Bridge Matching for both the S-tunnel and V-neck challenges. And especially under those quote-quote conditions where things are a bit off, Feedback Schrödinger Bridge Matching consistently achieves much lower W2 distances, for instance, 0.67 versus a massive 8.87 E plus 5 for GSBM. This numerical data strongly supports the visual improvements. So beyond just the improved accuracy we saw with the W2 distance, this next figure tackles efficiency. It's a bar chart comparing the training time as a percentage for Feedback Schrödinger Bridge Matching against GSBM, again for those V-neck and S-tunnel crowd navigation tasks. GSBM is the blue bar, effectively our 100% baseline. The orange bar, for Feedback Schrödinger Bridge Matching, is significantly shorter, about 40% for the V-neck and roughly 67% for the S-tunnel. This clearly shows that Feedback Schrödinger Bridge Matching is not only more robust, but also considerably faster to train. Alright, so we've seen that Feedback Schrödinger Bridge Matching is faster to train. Now, this figure here. Figure 8 shows us some really interesting image translations performed using their method. We see several pairs of faces. For instance, there are woman-to-man and man-to-woman transformations, and also old to young and young to old. Each pair shows the original image and then the transformed version. This visually demonstrates that Feedback Schrödinger Bridge Matching can produce compelling and realistic-looking changes in these high-dimensional image translation tasks. Building on those image transformations, this next figure explores how the amount of pre-aligned data, specifically those key point samples, influences both training efficiency and accuracy. The top chart shows training epochs. That's the number of full passes through the training dataset. We see epochs generally decrease, meaning potentially faster training, as the percentage of aligned key points increases before leveling off. The bottom chart revisits the W-squared distance for the S-tunnel. Noticeably, for the perturbed mean scenario, the W-squared distance, our measure of accuracy, dramatically improves with just a few key point samples, being lowest around 2.5%. So, this ability to leverage just a few key point samples for significant accuracy gains, as we just saw, really highlights the core idea here. Wrapping up on Feedback Schrödinger Bridge Matching, its key insight is the smart use of partial information. This semi-supervised approach, meaning it doesn't need all data perfectly paired, helps transform data distributions, like morphing one dataset into another, more accurately and much faster. It also improves generalization, the model's ability to handle new data well, and is a promising direction for AI where perfect data is rare. That's all for this segment of AI Research Roundup. I'm Alex, thanks for listening.